So yeah, before we start, has anyone heard about WebAssembly before? Just raise your hands. And anyone heard about eWASM? Anyone used eWASM? How did you use eWASM? It's not ready yet. Okay, so yeah. So what eWASM is, it's Ethereum-flavored WebAssembly, or rather, we're going to try to use WebAssembly in Ethereum. So my name is Alex, or Exec on GitHub. Mostly I contribute to Solidity and the eWASM project, but I also, from time to time, work on Ethereum.js and CPP Ethereum. And you would see with all the other talks that probably people from all these projects are kind of involved in eWASM. I try to gather everyone in these projects to join eWASM. So finally, after like 2 years, we can release something. You may have seen it in the agenda that it's going to be, I guess, 3-4 hours today. The entire afternoon is dedicated to eWASM. So I'm going to talk about a small intro, I guess 15 minutes. And after me, Martin, who's sitting on the left, is going to take over. And his talk is going to be really interesting because he has the flexibility of not dealing with Ethereum, and he can do whatever with WebAssembly, and he can do really nice things. After that, we're going to have a demo of eWASM, delivered by Jared. And after the demo, you're going to probably understand what it does, and you're going to get a bit more explanation how it works internally. So EVMC is one part, and Hira is another part. And finally, Everett's going to talk about the K framework and how someone can implement eWASM in the K framework. Then finally, a coffee break. I think it's going to be well-deserved, probably 2 hours at that point. And after the coffee break, we're going to have at least 1 hour of panel discussions and Q&A. So I don't think we have time to do a Q&A between any of these talks, but we're going to have a lot of time to have a Q&A after the panel. So if you have any questions, either for the first talk or the second one, please come back. If you don't stay here for the entire time, please come back for the panel and ask your questions then. Okay, we just take a step back first and look at the history, how we ended up with WebAssembly. So like in 2009, when Bitcoin was created, there was the Bitcoin script, which was able to do a couple of things. But quickly enough, they have removed some of those instructions, some of those things Bitcoin could do. And stepping forward a tiny bit more, Bitcoin was even more restricted. So they took in the client, they decided that a couple of script templates are going to be the one accepted by Bitcoin. And those templates are like 4 different templates, sending Bitcoin in like 4 different ways, and that's it. You cannot do anything else. So obviously, people weren't happy with that. So a couple of forks were created. The first one was Namecoin to extend the functionality of Bitcoin. But it quickly turned out that forks may not be the best idea. So a second option was to hijack one instruction in Bitcoin script called upReturn, because anything put after upReturn is ignored. So you can put whatever data you want there and do whatever you want. Well, not much actually, but you can put references to other things. And so like colored coins were implemented, but you couldn't do anything else with Bitcoin. So finally in 2015, Ethereum was designed and released. But quickly it was realized that maybe not everything was designed in the best way. So in Ethereum, we have cost for each instruction. And there are a couple of really useful things a contract would want to do, namely hashing or finding out who signed a message. And if you implement that in the EVM itself, in Ethereum, and measure it with the rules we have for gas usage for instruction cost, it's going to turn out that it won't fit into a block, because the cost of it is more than a block gas limit. So people came up with this idea of precompiles, which are basically just discounted contracts. So we have fixed costs for the contract, and they do a lot more than they should do for that cost. And I think all of these were like issues, and we tried to fix those issues. And we are going to try to fix those issues with WebAssembly. So hopefully 2018 going to be the year for WebAssembly. Okay, a bit about EVM itself. I think everyone in the room probably knows most of these things about EVM. But basically, we have 256-bit stack items. We have a lot of high-level instructions. We have a couple of basic instructions. And I don't really like the high-level instructions. Like one of them is SHA-3, which isn't SHA-3. But it's super high-level. It doesn't really have to do anything in a VM. All of that are these high-level things are in the precompiles, which aren't nice either, but at least they're not in the instruction set. Another problem with EVM is we have only a couple handful languages working with EVM. And I mean, it must be clear, based on all of these, that it's not really modeled after an actual computer. It is just a magical computer. I don't really like any of those. But there are like 3 main problems which probably should be fixed. One of them is the large stack items. And that actually is a problem because you cannot easily map that into a single computer instruction. It has to be multiple instructions. And that means in every single computer, every single client implementation, you're going to have different set of instructions doing that. So there's no real simple way to come up for a fixed cost for it, because every single client is going to have a different actual physical cost for it. The other really big problem is we have those high-level instructions. It's even harder to come up with proper gas costs for those. And the last thing is we do all of these gas calculations, all of these instruction costing at runtime. It's even, again, really slow. So hopefully WebAssembly is going to fix all of this. It tries to map a normal computer, so it has 32 and 64-bit stack items and operations. It doesn't really have super high-level things. And one interesting fact is it has been designed by a W3C working group with over 600 people. But it actually has been agreed on, and it has been finalized, at least version 1. Despite thinking it's designed by a committee, it still has been finalized. It's supported by all the major browsers, and at least there's 6 other implementations of it. I guess like 3 implementations in C, 1 in Go, 1 in OCaml, a couple of others. It's supposed to have a lot more languages supporting it, so a lot more languages can be compiled to WebAssembly. And yes, as I mentioned, it tries to really model a regular CPU, so it should be really easy and simple to map every single instruction to an actual CPU instruction. Okay, did we change anything in WebAssembly? Like, this is the first question ever. So we say we do eWASM. Okay, so how different it is to WebAssembly? We didn't change WebAssembly at all. We took the same WebAssembly you get, and we don't change it. The reason we can do this is because WebAssembly is quite flexible. In any WebAssembly bytecode, in any little piece of code you have written and compiled to WebAssembly, you can import external functions. You can import external features. And everything Ethereum has, all those things to access the state, modify the state, are implemented through external functions. And we call this specification the Ethereum Environment Interface, or EI for short. And that's the only addition we have to WebAssembly. We don't add new instructions. We don't remove instructions. And now you may ask, what do we do with parts we dislike in WebAssembly? Well, we don't remove them. We just have a process of validating the contract at deployment time, and we just simply reject the contract if we don't like it. So, for example, if it tries to do what we believe would be non-deterministic, a certain floating point operation, we can just reject the entire contract. Well, the fact for now is we just reject any contract which tries to use floating point at all. This may change in the future. We may be able to work around it, but right now we just reject it. And this just also shows it's quite flexible. The other big thing we have done is metering all those contracts at deployment time. The reason for that is we don't want to change the VMs, so we cannot really do runtime metering. We have to do this before it gets to the VM. So that's an example of all these external interfaces I've mentioned. So that's like one interface, get sender, get call value, etc. And this is an example contract. We just load the storage item for the sender address. We increase it by the value sent, and we store it. So it's like a mapping function. You can imagine compiling this code to WebAssembly, and any language could be mapped to this kind of behavior. So the next really important part is the metering. And the way it is done in EVM, it's a runtime metering. So whenever an instruction is executed, we have to calculate how much gas it's going to cost. We have to deduct it. And if we run out of gas, we have to handle that as well. However, VMs are flexible in this, so they could do it differently. They don't actually do it differently, but they could. There's only one VM which does it differently, which is EVM JIT, which kind of does the same thing we're going to do with WebAssembly. Which is, we are just taking, yeah, the jump test. Yeah, so basically, if you're familiar with EVM instructions and jump destinations, any code between the jump destinations will be executed as they are. So you can just break up the code by the jump destinations and calculate the gas usage for each of those blocks. Practically, we do the same thing for WASM. We just call it branches. So anything between branching instructions, we just calculate at once. So as an example here, this is a example WASM code in like a text representation. So it's the if statement, there's the condition, and the two sides. So we can just calculate all of the costs of this, and this, and this, and insert these simple statements, and we don't have to do runtime metering. So WASM going to have a much wider language support. I mean, that's what we claim. Obviously, it has this text format you have seen here. You could write WASM contracts this way, but you don't have to. You can also write them in C or C++ or Rust. All of this is working already, but there are plans to support compiling Go to WebAssembly and a couple of other languages. Unfortunately, even though it's called WebAssembly and it came from the browsers, JavaScript cannot be compiled to it. Yeah, I mean, that's probably funny, but one thing which probably going to be coming up is a question, what can you do with Solidity? Because most of the contracts currently are written in Solidity. They going to be compilable to WebAssembly. Yeah, it is the same text format as in the previous example. Basically, this is a function, and you do whatever you want in that function, and you can import the Ethereum methods like this. So as I said, this is one of the options to create contracts, probably not the best option. Here's another one to do it in C. I guess it should be familiar to anyone writing C. The most important part, why is any of this good at all? I think mostly in the past year, the main reasoning here was it's for scalability. But I think the main reason here is to have a more flexible system than what we have currently with EVM. As you can see, we have like imports, and we don't have high-level instructions in WebAssembly. So whatever new features we have to add to WebAssembly can be done via imports. And if we have to remove something, we can just change the deployment time validation contract. And we can say, this feature we had so far cannot be used anymore, and we just reject contracts having those. With EVM, it would be a lot more work to do any of these. Of course, a lot more languages. And most importantly, right now, a lot of effort is spent on creating EVM implementations. For every single language, for every single client, they have to create an EVM implementation. And for every language someone is designing, they have to also be able to compile to EVM. So if we cut out EVM entirely here and just rely on all these other people creating compilers and VMs, then we don't have to do it. Like the last point, that this is a better foundation for the future, is more like for the extensibility part. It should be really easy and simple to extend it. I mean, you may ask, what can you do with the current EVM? And this really comes up, and we don't really know the answer to this at all, how eWASM going to be deployed, right? So that's the main question. Will it going to be deployed on the main chain? And if so, will it coexist with EVM, or will it be deployed as a shard? And if it will be deployed as a shard, will it have EVM support at the same time? We don't know. But either way, we have this project called EVM2WASM, which can be used to run EVM bytecode on a pure eWASM VM. So whichever of these options is going to be, we have a solution for those. That's just a summary of where we are at the moment. So basically, we have finished implementation in CPP Ethereum, and there's an implementation in Go Ethereum ongoing at the moment. We just need to decide on 2 final tiny, I guess it's tiny, design decisions. And once we've done that, it's really just a metering contract left. But of course, the majority of the work left there is testing and figuring out whether we made any mistakes in the design. So if you're interested in eWASM, either reading more about it or contributing to it, please check the GitHub. There should be the design document and all the other source code. If nothing is clear there or something is not clear there, you can join the Gitter channel, and hopefully we're going to be able to answer all your questions there. Thank you.